we're going to talk about some of the missions that Goddard's doing. So I wish we had time to tell you about everything that NASA is working on, but that would take days to talk about. There's lots of different missions and things happening. But specifically, Goddard focuses, our location, Greenbelt, focuses on the Science Mission Directorate of NASA. And so along those lines, we are looking at earth science, planetary science, heliophysics, and astrophysics. So I'll tell you about 2 or 3 missions in each one of those different areas, just to give you a nice broad view of what we're doing here at Goddard. So to begin with, I'm going to play a video for you so that you get an understanding and see what's going on at Goddard from the voice of our scientists and engineers. Oh, and I'm going to turn my camera off as well. Oh, DJ.
At NASA Goddard, we build
At NASA Goddard, we study the sun's dynamic behavior and the space weather that it generates so we can protect astronauts and satellites in space as well as our technology on the ground.
At NASA Goddard, we use the data from a constellation of satellites to generate global maps of rain and snow pummeling the Earth.
To monitor how greenhouse gases move through the atmosphere.
And to model all of the Earth systems to create a dynamic portrait of our planet.
We launch small rockets carrying university-developed experiments into space.
And provide low-cost space platforms for testing new instrument concepts and engineering techniques.
At NASA Goddard, we ensure every craft is space ready.
We blast noise and shake instruments to simulate stresses at launch.
We expose them to the unforgiving vacuum of space and to the powerful magnetic fields.
At NASA Goddard, we develop and maintain communication links between Earth and spacecrafts in orbit.
We evaluate and improve system software to reduce risk in our missions, large and small.
Innovation and science never sleep.
And new discoveries never get old.
At NASA Goddard.
All right, so as you can see, we have a lot of different things happening here. So one of the things that makes Goddard so special, if we're looking at this map, is that we actually encompass 6 locations. So this shows you all of our NASA centers around the United States. It doesn't show you all of our specific smaller facilities as well, but one of the unique things with Goddard is that we are actually 6 locations. So we have our location here in Greenbelt, Maryland, which is our main location. And then in addition to that, we have Wallops Flight Facility on the coast of Virginia. We have the Katherine Johnson IV&V facility in West Virginia. We have the Goddard Institute for Space Studies in New York. And there's also a location in White Sands Test Facility, and there's one in Texas as well. So lots of great things are happening with Goddard. And so even in the states where we don't have official NASA centers, there's lots of partnerships with universities and companies and countries all around the world. So this next picture, this is our location here in Greenbelt. This is where DJ and I currently are. So we're in the top left corner up where you see that rocket up there. That's our visitor center. So that's our rocket garden. But right in the middle is our integration and testing facility. So there's the white buildings you see. So that's where our testing facilities are and some of our smaller clean rooms. But then the big rectangle building that you see with the blue lines on it, that's our large clean room space. And so one of the things I love about Goddard is there's so many different people, lots of things going on here. So we have about 10,000 people who work here just at our location. And we do offer internships as well in all of our different areas, from all of our sciences and our engineering, but also, with our communications office and our business and administration team. And so there's a lot of different ways of getting involved and engaged with Goddard. So this next picture is showing you inside of our clean room. This photo was taken several years ago when we were building the James Webb Space Telescope. You can see it in the back where the triangle is coming up. That was the front part of the mirror for James Webb Space Telescope, and the mirrors were being installed at that point, so they were laying down flat. So yes, this is our clean room. It's one of the largest ones in the world. It's 8 stories tall. It's massive. The squares that you see on the left side are filters. We're able to filter out something that's 300 times smaller than a human hair. And we rotate the air throughout this room, recycle it 42 times every hour. So this is a class 10,000 clean room, meaning there's less than 10,000 particles per cubic foot. So it's definitely a very, very clean place, because it's very important that nothing from us ends up onto our satellites before we send them into space, because we want to make sure that they stay clean. It doesn't cause any errors in function for the satellite as well. It's also a question of planetary protection, because we do build some different items that are going to be included on rovers and things that are going to other planets. So we want to make sure, again, that nothing from us could cause a problem for another planet. So that's another reason we use our clean room space. So this next picture is showing you our testing facilities. So we have to, as you saw in the video, we're testing for a lot of different things. The first one is we're making sure that it functions and works the way we want it to work. The other thing we're testing is we're testing for the stress of launch, because we need to make sure that our satellites are going to be just fine as they're being launched into space, because it's not the most gentle of rides up there, because you're in the nose cone of a rocket and you're going about 7,000 miles per hour as you're being launched up into space. So one of the first tests that we'll do is the one in the middle. It's our vibration chamber that you see there. So we'll mount our satellites onto that circle you see inside of that white frame, but the silver circle towards the bottom, we'll mount the satellites on there, and then we shake it like crazy. Basically, we shake it about 3,000 times per second. And so we're doing that to make sure it's built really solid and very sturdy. So again, that nothing will break and it will be fine during the launch into space. The image on the right with the red frame, that is a giant speaker. It is about 4 stories tall, 3 or 4 stories tall. It is the largest, loudest speaker I've ever experienced in my entire life. But what we do is we suspend our satellites in that room, and then we blast the sound of a rocket launch at it to make sure that the sound from the rocket doesn't cause problems. Because, as you know, sound travels as waves and it causes vibration, and the vibration's how we hear. But that's why sometimes you hear, like, go to a concert, you can feel it in your chest, or if something really loud, like a plane or jets flying overhead, you can feel it. So yeah, we have to make sure that vibration will be fine. Then finally, on the left is our space environment simulator, or it's our large thermal vacuum chamber. So it's very big. The top part that you see there is about 2 stories tall. It goes a story deep into the ground as well. And we use this to make sure that our satellites are going to do fine out in the environment of space. So it's very aptly named as a space environment simulator. So the top part comes off, the curved part, it slides over on the rack that you see at the top. We lower our satellites inside of it, and then we put the top back on, we seal it up, and then the cylinders you see around the outside, that is what will pump out all of the air. So it mimics the vacuum of space inside of his chamber. So we can test for issues with vacuum, but then we're also testing for thermal questions as well. So where you can heat this to about 300 degrees Fahrenheit, we can also cool it down to about minus 320 degrees Fahrenheit. To again, make sure that all the different aspects of the satellite are sound and ready to go before we launch it. Okay, so we're going to talk about a few of our missions within each of these 4 areas. I wish we had time to talk about all of them. And even this graphic is from 2018, 2019. So it's a few years old. So we have added a few since this point as well. So there's lots of amazing things and lots of great research happening here at Goddard. So we're going to start with our Earth science missions. And to begin with, DJ is going to tell us about our fleet of satellites around the Earth.
Oh, sorry. So starting with our favorite planet, the one we're standing on, NASA studies all aspects of Earth science from Earth, from vantage points of space, aircraft, ships, and scientists on the ground all over the world. NASA Earth Observation System is a coordinated series of Earth orbiting satellites for long-term global observations of the land surface, biosphere, solid Earth, atmosphere, and oceans. The EOS is made up of 26 satellites that have orbited or continue to orbit the Earth since the program began, with the first satellites launched in the 1990s. We're going to take a closer look at two of these missions, the GPM and ISAT-2. So one of the spacecraft that was designed and built and tested here at Goddard is the core observatory, what you're seeing in front of you, of the GPM mission. That was launched in 2014. The GPM mission uses 9 international satellites provided by the United States, Japan, France, India, and Europe. The core observatory, which is what you're seeing in front of you, orbits the Earth every 90 minutes, measuring every kind of precipitation falling from the sky everywhere in the world. We make this data public within 1 hour from receiving it. There are 2 main instruments on the board that provide us with that information. The first is a GPM microwave imager, which you see rotating in the top. It operates like an X-ray. It can differentiate between liquid water versus ice. Each object, such as rain, snow, and Earth surfaces, emit or scan this energy based on the object's temperature and physical properties. Secondly, you have the geofrequency precipitation radar, which you see underneath, that operates like a CAT scan. It can provide information as to how many raindrops of different sizes are in the cloud layers and how they're spread throughout the storm system.
So this is a specific example of what GPM can do. As DJ mentioned, GPM can look through a storm, it cuts through it, can see all the way through, it can see the different types of precipitation and also the intensity of that precipitation. So as you see here, the light blue material at the top, excuse me, is ice, and that ice transitions to water vapor, which we can tell from the GPM scans, and then that acts to power our storm. And that is something that we didn't know before the GPM mission. So again, if you look at the light blue at the top, the strongest parts of the storm, the most intense parts are right below it. So hopefully that can help us to better predict and track these storms moving forward.
Get my microphone on. Another important mission that was designed and built here at Goddard is ISAT-2 with its incredible laser. ISAT-2 is currently mapping the height and extent of all the ice in the polar regions of the Earth, as well as glaciers in the mountains, the height of trees in the Amazon, and even the health of the coral reefs, as the laser can shine down many feet into the water, about 30, 40 feet. The satellite has a single laser that is split into 6 beams as it leaves the bottom of the spacecraft. We then start the stopwatch to time how long it takes for that laser to reflect off the Earth's surface and back to the spacecraft. We can measure the thickness of the ice down to the width of a number 2 pencil. The laser sends 10,000 pulses a second, each pulse sending 300 trillion bright green laser photons to the ground, yet only a dozen will make it back to the spacecraft. We know our planet is changing fast each time we measure it, and ISAT-2, as well as our other satellites, will help us get ready for rising sea levels, more extreme weather, droughts, and changes in the atmosphere. With so many observations coming in from our science fleet, it takes one of the most powerful computers in the world to keep track of it all. We intake over 1 million observations each hour and feed the information to a computer that puts it all together, allowing us to create computer models of how the Earth works, from our atmosphere to ocean currents to changes on the land. These models will help us understand how the Earth works as a system. Everything is connected, as well as how the Earth might change in the future. What you're seeing is a model that produces a global numerical weather forecast on a routine basis. Goddard is home to the state-of-the-art supercomputing facility called the NASA Center for Climate Simulations. Goddard's high-powered supercomputer can perform a staggering 160 trillion or more calculations per second.
So this is another type of model that we have here at Goddard, and it shows us sorry, my mic was weird. So it shows us, this one in particular is showing us the Australian bushfires from the end of 2019 and the start of 2020. So you can see the date and the timestamp at the top. So just as DJ mentioned, the Earth is connected, so no continent really is a silo. So this is a really good example of that. This one in particular is showing aerosol optical depth. So if you look at the bottom, you can see the key down there. We're looking at carbon, sulfate, dust, sea salt, and nitrate. You can see how everything is moving through our atmosphere. So aerosol optical depth is the particles in our atmosphere, basically. So yeah, again, we can see what's moving around, particularly if you're looking at Australia, you can see the carbon coming off of the fires. So we can pay attention to how the atmosphere is moving and the patterns and how that's contributed to the spread of the fires as well. So hopefully this can help us to better track and predict, potentially other situations like this in the future. Okay. All right. And so now we're going to look at our planetary science missions. The first one is the Lunar Reconnaissance Orbiter.
Sorry about that. The Lunar Reconnaissance, So the Lunar Reconnaissance Orbiter has been orbiting the moon for more than 10 years, exploring all aspects of this fascinating world and helping us get ready for humans returning with their Artemis mission starting in 2025. LRO was envisioned as the first step in the return to the moon to study in greater detail. The main goal of the LRO is to create a high-resolution 3D map of the moon and to prospect for resources like water and to measure the radiation environment for astronaut safety. So we're coming up to the South Pole. So part of the LRO mission was including sending a satellite named L-Cross to research the possibility of presence of water ice on the moon. First, the spent fuel tank from LRO was directed to impact the moon. The debris plume that was thrown up by the empty fuel tank was studied by the L-Cross satellite before it too crashed to the moon, creating a second debris plume. The data proved there's water on the moon. So this is where we're planning to land in 2025. It's near the South Pole. So besides that, we're looking for other minerals that could be used when we establish a permanent moon base. So we're going to go to a place called the Astartes Plateau. So this is 40 kilometers in diameter, and it contains an abundance of luminant ilmenite. So you're going to see it come up on the screen. You're going to see a rectangular area in orange. So this is a mineral called ilmenite, this orange area. A mineral contains oxygen, iron, and titanium. The mineral can be used for making air to breathe and also rocket fuel. So to give you an idea how good the images are, were taken by this LRO spacecraft. Now remember, this LRO spacecraft is flying about 31 miles above the moon's surface. So from that height, we can see all the way down to the moon's surface, and you can see the last Apollo 17 lunar landing site. So you're going to see the rover, you can see the lander that brought the astronauts to the moon. So we've taken images, the LRO has taken images of every single Apollo landing site from 11 to 17. So we're going down. So you can see all the way down to the moon's surface. You can see that in the middle is the lander. That's what brought the astronauts to the moon. The bottom half always remains there. The top part are the ones that brought the astronauts back to the command capsule and brought them back home. There's the rover, and you can see the tracks in between. So really highly detailed maps taken by the LRO spacecraft.
So LRO has been fantastic for helping us to plan to move forward, to go back to the moon, to go to Mars in the future. And it's, helped us to learn a lot about our moon. But in addition to telling us about information for going forward, it's also telling us a lot about, how it's a record of everything that's happened in our solar system, because its surface hasn't changed for billions of years. So another type of small body out in space, in addition to our moon, that can tell us a lot about what's happened in our solar system are asteroids. And so this asteroid you see here, oh, can you hit the next button, Mr. There we go, Mr. DJ. Okay, so this is an actual video taken of the asteroid Bennu. It's spelled B-E-N-N-U. It was taken by OSIRIS-REx. And so asteroids are the remnants of the building blocks of our planets. So they can tell us a lot more about, again, what's happened in our solar system. So OSIRIS-REx went to Bennu, and one of the largest boulders that you'll see on here, I say boulder, but it's about the size of an Empire State Building. So it's like a massive stone, piece of stone. I don't know, boulder is not the right word. It's a stone mountain, if you will. But so OSIRIS-REx flew down to the surface. We're gonna go to the next picture, Mr. DJ. So it flew alongside Bennu. It took these amazing images for us. It mapped it, got some great research, and then it went down to the surface. So the point of the mission for OSIRIS-REx was to get the information and document Bennu, but then also to gather a sample. So the arm that you see coming out the bottom is about 3 meters long, or about 9 feet or so. Went down to the surface, it touched briefly, it blew out nitrogen gas to stir up the regolith, or the top layer of material, and then it gathered in as much of a sample as it could into that disc you see on the bottom. Then it backed away to a safe distance away from the flying debris and put the sample into the pod that you see on the top. And now that pod is what's on its way back here to Earth. So we're looking at the moon, we're looking at asteroids, so we can have a better understanding of the story of the conditions that allow life to arise. And so another way that we're doing that is we have our mission Dragonfly. So Dragonfly is an octocopter, or a drone, if you will, but it's about the size of a car. So drone doesn't feel like the right word. It's about the size of a 4-door car, and it has 8 rotors. So Dragonfly is going to fly around to hundreds of locations on Saturn's moon Titan. And we selected Titan because we believe it has an atmosphere similar to that of ancient Earth. So it can tell us, again, a lot about the conditions needed for life to arise. So potentially, can we look to see if there might be life that potentially be happening on Titan, or we can look to see if there was life on Titan, things along those lines. So we're going to be doing research there. So it has a whole suite of instruments on board. So it's going to be able to do chemical analysis. It's going to have things so it can sense, like it has a seismometer, so it can tell if there's moonquakes, what's going on underneath the surface. And it also has a suite of meteorological sensors as well to tell us what's happening in the atmosphere when it's there. So pretty exciting stuff. All right, so now we're going to look at 2 of our heliophysics missions. And the first one is our Solar Dynamics Observatory.
Many missions to monitor the activity of the sun and track the material it throws out into the solar system. Since 2010, the Solar Dynamics Observatory has returned continuous ultra-high resolution images of the sun. High-speed cameras on SDO take rapid-fire snapshots of solar flares and other magnetic activity. These images are taken in ultraviolet and X-ray light, which is invisible to our eyes. One measures what the magnetic field does, and one measures the effects of the sun on the Earth. So we're going to go on to the next solar mission, the Parker Probe. So we launched the Parker Probe in 2018, which is the first spacecraft to orbit close to the sun and will give us a first close look at it. It's a 7-year mission that will bring it within 4 million miles of the sun's surface. The main object of the Parker Solar Probe is to learn more about the solar wind, a mixture of plasma, magnetic forces, and particles that spread across the entire solar system. The solar wind also travels at immense speeds. It leaves the sun at a speed of 500 miles a second. By studying the solar wind much closer to the sun, the Parker Probe will be able to tell us such things as what part of the sun is providing the energy source for the winds and how they can accelerate to incredible high speeds. At its top speed, the solar Parker Probe will be orbiting the sun at a speed of 430,000 miles an hour. That's like going from New York City to Tokyo in under a minute. It will also absorb temperatures of 2,500 degrees Fahrenheit. So Parker Probe is protected by a heat shield, which you see over here. What you see in the front of the spacecraft, that white thing, is a heat shield. It's a 4.5-inch carbon foam that's protected by a carbon plate at the top and behind it. So everything behind that shield is experiencing temperatures about 800 degrees or so.
All right, so now we're going to look at 3 of our missions for astrophysics, and they all have their main science questions, but in addition to those science questions, they also are all studying and have complementary studies of exoplanets. And so the first one we're going to look at is TESS.
So the transiting exoplanets survey satellites is a new exoplanet explorer that's surveying 200,000 nearby bright stars within 300 light years of Earth in search for exoplanets. To date, NASA has recorded over 5,000 exoplanets in the last 25 years, and we anticipate that we should find about 1,000 more each year. TESS has 4 large cameras that are arranged in a vertical strip of the sky called an observational sector. TESS sees each observation section for 27 days before rotating to the next one. TESS uses the transit method to find planets. by looking for a slight dip in brightness as the planet passes in front of the star. The amount of the dip and the length of time it takes to complete tells us the size of the orbit of the planet and an orbit. Tests must see 3 of these same dips of light from the object to be considered a planet candidate.
All right, so the James Webb Space Telescope. So we're all familiar with the Hubble Space Telescope and the amazing science it has done and that it is doing. So here at Goddard, we designed, built, and tested the next big space observatory, the James Webb Space Telescope. This was launched December 25th, 2021, and it took us approximately 30 years to complete, as it was a massive feat of science and engineering, and we hope that it'll answer many questions about our universe and also to help us see further than we've ever seen before. So the James Webb Space Telescope is about 3 stories tall. It's as big as a tennis court, and it's mirror is 7 times larger than that of Hubble. The James Webb Space Telescope will have the power to detect water, oxygen, organics, and maybe even signs of life in the atmospheres of exoplanets. So it also will have the power to observe stars and galaxies so far away that their light has taken over 12 billion years to reach us. This will give us a glimpse of how the first structures in our universe formed, how the first stars began to shine, and it'll accomplish this by using infrared light to observe rather than visible light. All right, and then our last mission is the Nancy Grace Roman Space Telescope. So I'm going to tell you about it first before I play the video, because this one does have sound in it. It's one of my favorite promo videos that we have here for NASA, and the sound just makes it. So I'm going to make sure to play that for you guys at the end. But I want to tell you about this. So currently we're working on building the Nancy Grace Roman Space Telescope here at Goddard, and it'll continue our work to explore exoplanets. So we also will be exploring a newly discovered phenomenon called dark energy. And we'll do this by looking out into the deep universe. So dark energy appears to be driving our universe not only to expand, but to accelerate in that expansion. And the mission may change everything we know about the origins and potentially even the ultimate fate of our universe. So it's a pretty amazing, and we're pretty excited for this mission. And so it's probably going to be pretty groundbreaking, you know. So it felt right that this was named in honor of Nancy Grace Roman. She was our first director of astrophysics at NASA in the 1960s, and she helped to lead efforts for other space-based observatories like Hubble. And so it felt appropriate to name such a potentially science-changing mission after such a great scientist and leader. So we'll go ahead and play this for you here. It's very short, but I love it. Yeah, so it's very short, but I don't know, I love the music. And then the part when it's like the universe will give us answers, I always love it. I'm like, yes, we will. It's great. Okay, so we go to the next slide, Mr. DJ. So that was the last mission we were going to tell you guys about. I wish we had upon hours to continue to tell you about all of our different research going on, but we do not have that much time, unfortunately. But so I know we spoke a lot and we said a lot of things. So I was wondering if you all had questions or if there's any information we could help share with you or anything else that you were wondering. I don't know if folks, if you want to raise your hand or if you'd prefer to type them in the chat, then that would be just fine as well. Or any thoughts you guys were thinking?
I did have a question. Ignore the sound of my upset 4-year-old in the background at the moment.
Oh no.
When you were going over the Lunar Reconnaissance Orbiter, you had mentioned about a permanent moon base. Is there a goal as far as the timeline to get that implemented, or is that going to be strictly like a U.S. project, or is that going to be an international project? Can you give us any details on that? Because that's kind of interesting.
So DJ's muted. So we're planning that we will bring humans back to the moon in 2025 and then continue to grow the base from there. I don't know if there's like a exact date, so to speak, where they're like, this is when we're done. But it's definitely plans from that point. So it could be kind of like a pit stop on the way to Mars is the goal, ultimate goal for it. So we'll have the base on the moon, but then in addition to that, we'll have Gateway. So it'll be kind of like the International Space Station that we have going around Earth. It would be positioned at the moon and it would be called Gateway. And well, and then so DJ, can you tell us, is there an international interaction with this or?
Well, we're definitely working with commercial partners like SpaceX and Blue Origin, which is Jeff Bezos' company. They're going to help us get us to the moon. They're going to build their landing ships. And so they're involved in that. And that will be completed by, we're going to be landing on 2025. I don't know exactly when in 25. And as Amanda said, we're talking about Gateway, that's 2024. We plan to put that up. So that's all I can tell you right now. We're still working on it.
Awesome. Thank you so much. Does anybody else have any questions for them?
I do, after Hannah.
So I see in the chat, what are some of the roadblocks to developing these advancements in telescopes?
Detector technology, materials used to make the mirror. The mirrors that were used in James Webb's beryllium O-30, and that has to be drilled out from the mountains in Topaz Ball Mountains in Utah, and it takes a long time to make each of those 18 mirrors. So that takes a long time. Also, the technology, the CC detectors, the cameras. Nancy Grace uses a mirror in its telescope that's 2.4 meters, which is the same size as what's in the Hubble, but it can see 100 times more field of view because of the technologies used in the cameras. So we are setting a 300 megapixel camera on the Nancy Grace Roman telescope. The camera that's on the Hubble is a 1 megapixel camera. So yeah, we try and incorporate all the latest technologies in our telescopes, but technology is moving so fast that when we're designing a telescope, there's already been newer camera, a better camera than what we plan to use for that telescope, but we had to stop any more development. Otherwise, we're never going to launch our telescope on time if we keep putting a new camera in, a new design every time this one comes out. So we freeze the design, and then yeah.
Was it William
Okay, we have
Warrington?
another one in the chat.
Okay. So Dragonfly drone is going to Titan. What types of sensors will it have? And what are the mission goals in brief? I guess the general mission goals is that it's to kind of get an idea of what's happening on Titan. So I know they want to do exploration and study for like chemical composition, what's the makeup of the ground and the soil and the things there. And they're also are planning to look beneath the surface to get a better understanding of any movement underneath the surface of what's happening in Titan, and then also doing a survey of the atmosphere as well. So loads of different kinds of sensors they have on board, lots of different suites of things to make it happen.
So radiation protection for the future of the lunar base. We're already developing materials that are X-ray proof, radiation proof. We're working with an Israeli company, a German company. So we have protection for the astronauts and also radiation protection. One of the ways we can protect the astronauts when they're living on the moon from any radiation coming from the sun or anywhere else is to build our base in these what we call lava tubes. So if you look at the moon at night, you see the dark patches? That's all lava that's come out of these lava tubes that filled up the craters. Those tubes are now empty. We can make that a new living quarters for astronauts to live in. We'll just have like 2 doors on either end of the tube, and they can live in that tube. And we can pump oxygen in that tube. Now, all the rocks that are above that tube is going to protect us from the radiation coming from space.
All right, any other questions, guys? Okay, so now that you have started receiving images back from the James Webb Space Telescope, has it been able to offer new insight or clarify any previous ideas yet? I don't believe they have necessarily released that information too much. I know they have released some of the images as well, but some of like the peer-reviewed findings and things along those lines, they haven't had to publish those just yet. They have, I believe, 1 year of proprietary research on those before they have to submit that information out, and then before it's just generally available to the public. So I don't remember off the top of my head if I've heard anything of any new insights yet. Have you heard anything, DJ, though? I think mostly it's just been, these are the images and this is what we're looking at. So some of the science hasn't been done. Did you say no, DJ? Sorry, I talked.
Correct.
Okay. All right. Any final questions, guys?
I have a question. Do you work at all with Jet Propulsion Laboratory out in California on any of these missions, or do you do different missions from them?
Yeah, so pretty much if there's any science mission that's happening within NASA, Goddard's probably supporting it in some way or another. So like, for example, the different Mars rovers and like Perseverance and things like that, we did support and provide help to them for that. So different things, different times. We love having a giant group project.
My sister's husband, Russell Knight, works out there at Jet Propulsion Laboratories. So a lot of what you're talking about reminded me of some of the projects he's, discussed and shared.
Oh, wow. I know. I love JPL. I got to go out there once for some meetings. It was pretty fantastic.
So some of the things that we work with JPL are like the experiments, like a gas chromatograph and spectrometers and magnetometers. Those are the main instruments we work with JPL that go on their missions.
Okay, that's neat.
You're welcome.
All right, see another question in the chat. So will the Europa Clipper mission feature a similar laser to that of ISAT-2? I do not know. Do you know, DJ? You do? I think you muted.
Nope.
Okay, we are not sure. You stumped us on that one. I'm sorry.
Awesome. Are there any last questions for them before we let them go on back to their busy schedule? I'm sure.
Well, great. Well, guys, thank you so much for inviting us to join you today. It was great getting a chance to speak with you.
Thank you so much for joining us. I really appreciate you guys doing this for us again. We learned so much.
No, you're welcome. You're welcome. We hope you have an amazing rest of your day.
You as well. Have a great evening.
Thank you.
Bye,
Thank you.
everyone.
Bye.
Bye.